Well, we're going to resume. As I was saying earlier, there will be 3 presentations of examples, case examples in France. In the beginning of the afternoon, there will be an example in Portugal presented, and then we'll take some time to discuss about the project. The 3 people who will now speak, that's Pont-à-Mousson, Fégès-Messon, and Save. Pont-à-Mousson, Marc Barbion is going to present to us his first, what is developed with his company in terms of power production from networks. Good morning, everybody. Pont-à-Mousson is a company that manufactures and designs pipe systems for the transportation of drinking water and treated water. As such, we are always looking for innovative solutions to perfect our processes and to improve our systems of water transportation. More and more, we try to increase the value of these transportation systems. It can be done in different ways, and one of the ways that I'm going to present to you today is to use part of the pressure that is in the water network to produce electricity. It's a simple concept. In drinking water networks or untreated water networks, there's pressure that can be dangerous for the end user, because if there's too much pressure in the network, the equipment can be destroyed, taps, washing machines, etc. So in some places, we've got to reduce the pressure, and this pressure reduction is never used. The pressure is dissipated and not used. The idea we had with our partners is to dissipate the pressure, but at the same time to manufacture, to produce power. So it can be a virtuous circle where the energy that is used to transport, to carry water, can be recovered, partly at least. The concept is simple. We make pipes at Pont-à-Mousson, so it was very logical that this solution be in a pipe. The main interest of this solution in pipe is that it's a technology that can work with counter pressure. That is, you may have pressure upstream of the turbine, which means that you can continue distributing water towards the end devices. It's a simple principle. You've got a pipe in which you have all of the traditional elements of turbine running, a turbine and a generator. The generator produces electricity thanks to the movement made by the turbine. The electricity can be used for self-consumption to power your nearby equipment. It can be the case of valves, but you can also power the power grid and sell that power according to the criteria of EDF. It's very easy to implement because it's a matter of piping. You cut the pipe and you insert that turbine solution. And then we've got all of the equipment to manage the equipment, because there can be issues regarding pressure management. So it can be installed in drinking water networks. There are laws in France that require a bypass in order not to disturb the distribution in case of problem, because it can have failures. So if it has a failure, we've got to be able to continue distributing water to the end users. It can also be installed, you can see on the screen, in any position, vertical, horizontal, so it simplifies its setting. It can be on the supply chain of a tank. There's a case in France where we power through a dam, a station, and we put that machine right before the treatment plant, because there's a lot of energy that is not used. The characteristics of the micro-turbine are very interesting for its deployment. It's a machine that is immersed. So the main interest is that, well, you may have a risk of immersion, but obviously there's no risk because it's already immersed. It is automatically cooled through the liquid that goes through it. So you don't have to have ventilators or motors that are noisy. So it's not noisy at all, and it produces no vibrations. There's very little civil engineering because it is installed in pipes. It just takes a few hours to install that machine. It's less than a day's work. As it is within a pipe and you can't see it, the components are very traditional. There's no grease, there's no oil. There's no control systems integrated, so it's very simple. Very little maintenance is involved. It works automatically. That is, that machine integrates through the control system all of the working conditions. You may have a disconnection of the network. It's going to stop or start automatically. There's a number of control elements that are such that it works automatically. It can be as long as 4 meters, and it can be as wide as 1,000 millimeters. It's got constraints, running constraints. It can work from 2 liters a second to 700 liters a second. For well, that's normally the conditions for drinking water. As for the delta pressure between upstream and downstream, that's the fuel really to run the machine. We can take as much as 1.5 to 25 bars. That is, you can have a machine where the input pressure is 25 bars, and at the output you have a neutral pressure, and it can and the power can be as much as 350 kilowatts. Maximum power is 500. 3 examples that show the way it can be used in a treatment plant. So that's almost a case study for this type of machine. The customer decided to self-consume the power produced because the selling price was not interesting enough. So it's self-consumption. So it's a drinking water treatment plant that consumes a lot of electricity. We have installed 3 machines in parallel. They work according to the chosen rate of the facility. It can be as much as 1,200 liters a second. Those 3 machines produce about 1.5 gigawatt hour of electricity a year, and it allowed that plant to have a self-consumption that is equivalent to 35% of their whole consumption a year. So that was built taking into account the location of the machines. Very little civil engineering, very little is required for this type of machines. We just made a bypass. Second case, a little machine that powers Sofrel box. We needed little power. It was installed in a valve field that didn't have electricity, so we applied the necessary quantity of water to make it run. It is in parallel to the pressure reducer, and it works according to the level of load of the battery. The idea is to always have a loaded battery. So there's a small valve, 24 volt valve, and the electrical equipment is directly powered. Last example, again, in a water treatment plant, valve room with a micro-turbine. It's a 110 kilowatt turbine, and the electricity was sold to the grid. Those are the 3 cases you may find with this type of technology. In France, it's of it's a lot of interest to many stakeholders. It's the start of the approach, but we're quite optimistic with regard to the deployment of this type of technology. Others will be presented, but I think there's a true will, a political will to deploy this kind of solution in the drinking water networks. I think that's it. Thank you. Do not hesitate to ask questions of the speakers. If you've got any, it's possible to answer a couple. Yeah, I just wanted to ask you a specification. You spoke about a recent project using the BiPAM turbine. Isn't it the Annonay project? Well, I was in Annonay yesterday. I didn't want to talk about it, but Annonay? Yeah, you're right. I mentioned it in the example I gave you. It's drinking water treatment plant with a dam. So that's 80 liters a second at 5 bars. The pressure being too high for this plant, the pressure is reduced thanks to an air-pick system. So the water goes through it, and you've got some kind of shower that reduces the pressure. And the idea was to be in parallel with this reservoir and to make this micro-turbine run. We implemented it, we commissioned it yesterday. The machine produces 27 kilowatts of electricity that is sold to EDF according to an H16 contract. The specialists will understand this. It's a contract that makes it possible to have purchasing prices that are interesting, that are attractive, prices that are valid for a period of 20 years. And that globally allow you to have a price that is 3 times what it is on the spot market. So the return on investment is 5 years for such a project. It was planned for this project to have a production of 132 kilowatt hour. Yeah, it is the case. Well, the machine will be able to produce that quantity of electricity now. The quantity of electricity produced per year depends on the running of the plant. So it is now the plant that requires water, but maybe tomorrow in the future, when the dam has got to be emptied without the plant being run, maybe we'll send directly the water to the turbine to increase the running time and to increase the production of electricity. But we should be able to reach the goal. Well, I'd like to specify for the audience that in the preparation of this day, I looked for projects, and I was directed to this one. The situation in Annonay is quite specific, because the lake is at 500 meters of high altitude, and the town is 150 meters under it. Well, yeah, of course, for electricity, if you don't have a difference of height, it doesn't work. Yeah, so we've got 5 bars and 80, and permanently 80 liters a second. It really is a case study. But 5 to 6 bars of pressure at input, and how much is the pressure at the output? 0.2 bars. Well, the necessary pressure for the water to go back. We have got to climb up about 4 to 5 meters. That's why we need a pressure of 0.2 bars. The micro-turbine is about 2 meters, and the intermediary tank. We've not changed the way the plant worked. That was very important for the municipality of Annonay that imposed to us radical specifications. The machine had to have an ACS because it's about drinking water, and it shouldn't disturb the running of the plant. And just another specification, the ideal pressure for the running of water network up to the end user, that's what, 5 bars? Well, no, for 5 bars, no, there's no ideal pressure. The pressure is related to the characteristics of the network. But you need a necessary rate, yeah, the rate that is necessary for transportation purposes. But there are drinking water networks that are between 1 and 2 bars of pressure. This type of equipment is not adapted then, because we consume pressure, and if we consume pressure, Well, that's energy lost in the moving of water. Well, if you recover energy, you lose some on the other side, yeah. But some people say, okay, we're going to increase the pressure of the network to be able to use the turbine. And we say, no, 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 it's useless. Okay, I'll stop here then. Maybe we can have another question and answer session afterwards. Good morning, everybody. I'd like to thank Yves Cabaret. I was asked not to speak too close to the mic. I'd like to thank Yves Cabaret, who invited us to present our achievements in reversible pumps. There are several ways to designate them: reversed pumps, reversible pumps, PAT. Achievements that we made for our customers in collaboration with them. It is a pioneering field, so we've got to collaborate with different parties. I will give you a more personal point of view because I've worked on the design of turbo turbines in pump manufacturers for a number of years. And I've qualified pumps for turbine running. So just to focus on our activity, our business is the achievement of water plants in a turnkey manner, be it for drinking water distribution, irrigation, electricity generation. We're quite sensitive to energy aspects in the framework of our projects. We've got our headquarters in Laval, not far away from here. So I'm going to present to you two projects that we made. The first one is in the Reunion Island. That's the interconnection of the irrigated areas. That was commissioned a year and a half ago. It works within the framework of this project. That was a pumping installation with a reversible pump out of the 5 machines. There's one machine that works for pumping and as a reversible or reversed pump. So it is an irrigation solution. The turbine is between 2 tanks with hydraulic conditions that are stable, which facilitates the use of this type of pumps. The equipment that we installed, it's a machine of 500 kilowatts that works with a 4-quadrant variator, so it makes it possible to work both ways with speeds that are different. The installation to recover energy, the energy produced is not self-consumed. We produce 150 kilowatts. The energy is sent back to the network through a meter. The return on investment for this type of installation, I'm talking about the equipment, the pump, the motor, the drive line, the electrical closet and variator. That's about 4 years. I'm not talking about the building. It's not very legible, but it's just to show you On the left-hand side, you've got the characteristics of the machine when it works as a pump. It's a multicellular horizontal machine with a rate of 500 cubic meter per hour with a 500 kilowatt motor. So we were required to have this rate of 500 cubic meter an hour with 1,200 revolutions per minute rate. So we had to have a 4-quadrant variator, which makes it possible to run it both ways. For the second installation, the first one was brand new. The second is being completed for the Canal de Provence company. So we thank Canal de Provence to have allowed us to communicate about this project. That is in progress, and that should be completed within the coming weeks. It is about an existing network that will be equipped with a reversible pump. It's a drinking water network that uses gravity. We communicate between a tank and a drinking water tank that distributes water to the Seine-sur-Mer town, and the pressure in this work in the existing network. There are two pressure reduction rooms to reduce pressure from 17 to 4 bars. The client chose as for the first pressure reduction room to replace the pressure reducers with reversible pump solution. So it's the characteristics 450 cubic meter an hour. It is well, the electricity is also sent back to the network. There's no self-consumption. There's a asynchronous generator installed. We send back about 130, according to the hydraulic conditions, 130 kilowatt to the network. You see on this drawing the part that we redid. Well, the turbine line on the drinking water part, we've got to ensure the distribution of water even if the turbine fails, so we have got to have a bypass. That was done. We installed the turbine, the bypass line, and in the automation part, according to the conditions, either if the rate is too low, we work through the bypass, and then there are there's a possibility to work 100% with the turbine, and when the rate is higher, we work with the bypass and the turbine line. And the second part of pressure reduction was kept by the client. What you've got to know is that the client within that framework has got hydraulic data, rate and pressure that made it possible to adjust the performance of the equipment. They've got network conditions that are stable, that guarantee the possibility of operating 9 months a year. Then you've got ancillary equipment installed around the turbine. In the framework of this project that we completed, we did all of the civil engineering, but in fact it wasn't that much. we installed the hydraulic equipment, acoustic and ventilation equipment associated that wasn't planned to start with. The installation of new electrical equipment, in particular the generator with safety equipment associated to protect the equipment and the network. The modification of the electrical closets that existed, and in connection with the central station. I didn't have a nice photograph of the installation, but those are the tests, qualification tests we made. It's a multicellular machine, verticalized. In a general way, for this project, well, I'm not a specialist of administrative processes, but what we identified in the discussions with our clients is that the key approach is you've got to ask for administrative authorizations and permits. You've got to ensure the compliance of the sanitary installation. If it's for drinking water, the equipment has got to be compliant. But you've got to make a request of the authorities. And the second part that is not to be neglected, that's the measures to be taken before the project, upstream of the project, when you ensure that the works to be done can be done according to the closeness of the distribution points. And then in the execution, there's the electrical connection project that's got to be presented to entities so that they can make their own works. So we contribute as an integrator, either to give information to make it possible to compile those files and requests that are the responsibility of the engineering office. One of the key points is for the network to be able to receive the turbine. You've got to have rather stable conditions. The qualification of the equipment, that's also one of the issues. I would say today when you use the pump, the equipment is perfectly qualified, but when it's used as a reversed pump, well, manufacturers have not always qualified their equipment for this purpose. So sometimes you've got to initiate the approach, but people from the labs know that. There are laws that set the framework for it, but and it shouldn't be ignored. And the electrical connection to entities, that's something you've got to anticipate on during the preparation of the project, so that works can be done in due course when the equipment is installed.
Avantages et inconvénients.
Few advantages and disadvantages of these reversible pump solutions, according to us, in our own opinion, such is not representative of everybody's opinion, but the investment cost is very reasonable on catalog pump, kind of mid-range kind of pumps. The average cost of the reversible pump is the actual pump cost. It is an asynchronous model with an encoder with a view to controlling the rotating speed. So no overcost on the equipment in itself. So the ROI return on investment is, we're talking 5 years. In our case, it was 4 years on the Interco, and so that's something between, we're talking between 4 and 8 years. As these are reasonable cost. So reverse pumps is a standard product. So lead time, production supply lead times are relatively short, very reasonable, and hardly any maintenance, no technology related to the control and maintenance of these. So it's really ease of use, ease of maintaining. So this is a turbine design equipment with performance and as a pump. So it's we're talking 80%, so less than a cellular piece of equipment. So these are, we're talking about up to 250 kilowatts as applications. And that's pretty acceptable, very appropriate performance-wise. These advantages now of these solutions, they are, well, in case of big variations, classic solutions with adjustment controls can optimize the energy side of the performance, which we can't do with this type of equipment. So that limits the range of use of the equipment and the predictability in terms of the performance of the equipment has to be worked out, although the product is not initially designed to be used as a turbine. So you have to have good predictability, good forecast of the performance of the equipment. So there we are. This brings my presentation to a close. Thank you. So we're lagging behind, bit push for time, just a couple of questions, and then we'll hand over to Olivier Salascar from Save Innovation. Will be our next speaker. Any questions for Mrs. Deschamps? Well, it's pretty self-explanatory. Forgive my French. This pump. Microphone, please, says the interpreter. Project number 1 was pumping and turbining, and the second project is a replacement by a turbine. So this is just one turbining applications. So the purpose was to produce power. That's it. Production of power. So, and the Société Canal de Provence, our client, so has delivery stations. We call delivery stations, so they channel pressure before delivering or supplying reservoirs or delivering directly to the clients or customers. So reversible pumps have been installed on their installations. So it's not, the flow is not a river. No, it is within a network, within the pipelines. Yes. What is the head? We're talking 15 meters, so 15 bars in pressure. So we're talking 15 meters in terms of head. There are technologies around, so we can use either one or the other technologies for the purpose of this application. So we presented a number of applications, then with solutions in machine solutions such as the PAL solutions. But there are technologies. This can be in kind of a split using plan solutions. So there are a number of there is a number of possibilities around. Well, first of all, I'd like to hand over to Mr. Biyov. And then I think you have engagements to attend to. Yes, thank you very much. I will. I arrived late, and I will leave you before the end of this session. So I wanted to salute and really pay credit to your reflection, your projects. I can see a number of Interreg programs that have been developed one after the others, I think, over time. And this will be, and is said to be, one of the good Interreg projects. And I think we need to recall that the discussions for the renegotiation of the multi-annual financial frameworks in full swing. These benefit from allocation of the FEDER, so European Structural Fund, and so funding resources, and these are then interwoven with common agricultural policy funding as well. So it is interesting to really focus on the way you achieved those results. This is really important for the Parliament to have really concrete, practical examples of good Interreg project to showcase. So as to get, to show that we can get money for our bucks, and sustainable development in it, and it's as standalone topics would be worthy of a full day of discussions, but it's about optimizing of efficiency and response with a parsimonious use and of the resource, so energy saving, energy optimization, because if we, on a business as usual basis, if nothing is done about it, then the users' bills will be going up and up. Now, and this brings to the next topic, the concept of data ownership. As you go along in this project, you will obtain a number of data. And this, and I think within this Interreg project, it is important for you to develop partnerships with the academic world. And it is through these partnerships between joint water authorities, power operators, and universities. This is how you can develop a project, and really, which brings me to the next point. I think that over time you will end up developing standards, and as you go along, I think we need to have at the European level a harmonizing and a converging of these standards. And this is how you become stronger in a free trade agreement. If European Union goes really to fast-paced towards free trade agreements, if we can develop those. I mean, some countries have turned inwards. When China is like a sledgehammer via the Silk routes, and I think that if we go in that directions, I think chances are that these European standards will become global standards. And there will be a lever, a tremendous lever for the operators already committed and engaged in this process. And so don't hesitate, I think, quite sincerely in terms of outcome, results, practical exercise. Many Interreg submissions which we review at the European Commission don't have this level of practical use and efficiency. So thank you very much once again. Dear elected politicians, dear President, dear chairs, ladies and gentlemen, good morning. I'm most honored to participate in this event to present the our solution for the water networks. So very clearly, let's focus on the company I represent, Save Innovations. So we are startups. We came into being in 2012, and we are based in Grenoble in France. We've been France Entrepreneur laureates, award winners, and we're supported by Tenertis, the national startup incubators, and so particularly focusing on water startups. What is our technical solutions? What have we developed so far? We developed what we call a micro-turbine, because it doesn't consume much electricity, and this is the so this turbine has been developed in France, and for applications internationally, this is a turbine. We're talking about a 20 centimeter diameter pipe that can adapt to various pipelines and networks. And this is the only turbine producing electricity at very low water flow. And that allows to use a source of energy, a storage of energy that is, that can exploit not used and available energies, and that allows to produce the required power at the points of consumptions and at any points within the networks. So without getting too much technical about this, I don't want to snow you under technology inputs, but there are two technological families our patents rest upon. So we have, first of all, a disruptive technology applied to alternators, allowing to turn hydroelectricity into power. So we've developed products that can be easily installed on pipelines with reduced maintenance, and which is really practical and user-friendly for the water operators, network operators. Every product has its advantages, but our turbines do not need any bypass. It is installed as a valve, as a regulating valves, and for this, to that end, we have patents based on the installation of bypass within the turbine. So when there's an overpressure, so when fire brigades need a strong supply of water, so all of these regulating, all of these alternator will just be bypassed so as not to damage or create an issue with the flow or the water distribution. Now, what is the market? This product is designed for what type of applications? So this is what we call smart water or smart water networks. That requires to get control and real-time management and control and real-time, really, according to what we've heard from the market. This is going to be more and more important to control the water within the networks. Well, what do we mean by controlling, managing? First of all, limiting the water leaks. And we're talking about currently 30%. We're talking, water leaks account for 30% of within the networks in France and internationally, and as well as by management, we mean management of water drinkability, controlling the physical, chemical quality of water in real time, data transmission of the data to data, transferring data to data centers. So data really lies at the heart of the problem, or is a crux of the matter. and to generate data forward these data to data centers. We need some electricity, some power, but not that much. And for operators, we already talked together here. Those operators want autonomous solutions in terms of controlling and measurement instruments, smart solutions there. So to summarize, the need is about coming up with an autonomous solutions for the purpose of transfer of data anytime, anywhere on the water networks. So our solution is a Pico turbine that provides a standalone power supply suited for isolated areas, so we can have power when we can access electricity via the energy utilities. But at all points within networks, including isolated areas and in areas with low flow sites and low available pressure drop. So we're talking about delta P and 0.1 bar. So no pressure related issues. So that's an installation. Our turbine is the first white box before the flow meter. So this is online, and to its left, the a schematic representation of the turbine on the pipeline that feeds in via a control box that's been developed by a company that contains sensors, analyzers online, and data transmission systems, as well as anti-intrusion systems for the safety of the site. And we are faced with lots and lots of requests, demands, notably in mountainous areas, and dams, dam control systems. So as to because you just need to kick a door open to get to the control the control cabinets or the control stations. So we offer a sustainable, renewable and low carbon energy solutions. So in the market these days, you can find measurement instruments with batteries inside them, but these batteries are not really green or environmentally friendly, and you need to manage their end of service life. That's something that we, this is an advantage of our system, and you want to avoid having power grid connections for remote areas. These are expensive, and these entail a high carbon installation costs. So this is about ensuring the water resource management, so eliminating waste and ensuring proper access to drinking waters to all the populations. It's going to be more and more a topical issue in the next few years, not necessarily in France first, but we see many countries where this drinking water is becoming an issue, and regulating monitoring of water resources for the benefit of the population. So we are very young startups, but we've come a long way. And these are the milestones of the story of our startups. So in 2015, we delivered the DN200 turbines. That really we developed engineering prototyping projects. So we qualified the characteristics of these turbines, the DN200, in 2016. We developed the proof of concept to validate on 2 pilot sites, both located in Haute-Savoie and the French Alps, and where the solutions was deemed as satisfactory. In 2017 into 2018, when extending our product range to other diameters, we're starting to run the pre-production, the pre-series. So we have a few tens of orders that we booked in since start of the 2017, and we're now industrializing in putting in place a production line in France, a manufacturing line in the Grenoble area in France, so as to reach volumes, and it goes in hand with that the market prices that we've managed to define and identify well. So these products, our products, is being now in phase of industrialization, and we are now So not only rolling this out on pilot sites, but on local networks managed by water authorities. So it took over 18 months to validate the proof of concept on pilot sites with pressure sensors, data transfer devices, control panels, IR sensors, and light station. And in our management and our control systems, we have real-time monitoring of the production of the turbine, consumption of the equipment of the on-site equipment, and the charging level of the battery. So the battery can be used as a buffer to always get enough power so as for equipment to all be supplied at all time. So this is a snapshot of what I've been telling you about. So 3 ranges, the N200, 150, 100. So in 2018, pre-series, into 2019, the series, so the produced equipment at market price. So what are we targeting? Well, first of all of the players in this sector, the equipment manufacturers, the OEMs, these are our targets, as well as the engineering agencies, private operators, and local authorities. We've been conducting discussions with local authorities, and this is about developing the awareness as to our products. So I'm preaching here today, and we have this market entails substantial players, and when you're a small player who wants to convince of the that the product is interesting and worth having on board.
And the Pico turbine is clearly a French new technology, but we are a European company, and the water issue is clearly a global and a European issue. So we are willing to address the global and the European markets. Thanks for your attention.
Merci.